Hello, welcome back to es346 Basic Thermodynamics. This is module 4.2, Closed System Energy Balance. The section in the textbook is section 4.2. Here are the two learning objectives for this module. At the end, you'll know the first law energy balance for a closed system, and you'll be able to solve for the heat addition and removal during the process using the first law. So first, let's go ahead and look at the first law energy balance for a closed system. So I have a closed system, means that mass does not enter or leave the system, but I can have heat and work being done. So I could go ahead and heat may be entering the system there, it may be leaving, I may have some in, some out, I might be doing some work, some shaft work into the system, it may be expanding, so there might be some boundary work occurring on the system. And so what I'm going to do to my energy balance is that I know the change in energy is whatever energy goes in minus whatever energy goes out. And so that change in energy, that's going to be the change in the internal energy, the thermal energy, plus any changes in the bulk kinetic energy of the system, maybe any changes in the potential energy of the system, and we're neglecting the magnetic and electrical. So that's sufficient for now. The terms that go in, well, I could have heat going in, Q in, I could have work going in, and so whichever Q or W arrows go in would be those terms, and then I would subtract out all the heat that leaves minus whatever work that leaves. Now, if I look at a system that is not making large changes in the net potential energy or the kinetic energy, so I don't have a tank that suddenly starts flying out or a tank that goes up in the air, I can usually neglect those terms and just have delta U, change in internal energy, which if I write in intensive variables will be M U2 minus U1, and that there will be Q in plus W in minus Q out minus W out. And recognize I may have the total work out could be two terms. That might be some boundary work as well as some electrical work, or I could have several work terms going in. You'll have to look at the particular system each time to determine which ones of those you need to include. All right, so let's go ahead and do an example. Here we got a piston cylinder. It has 2 kilograms of water. It's heated, so I'm going to go ahead and put a Q in here, and it's heated, so that means I've got heat going in. I know I have Q going in. The pressure is constant at 400 kPa, so I know P1, 400 kilopascals. It's constant, so I know its final pressure, P2, is also going to be 400 kilopascals. And we know the temperature increases from 250 to 500. So T1 is 250 degrees Celsius. T2 is 500 degrees Celsius. And it wants to know how much energy was added by heating. So it's asking me what that value of Q is. And I have a piston cylinder, so we can go ahead and move. And so it probably expands if I'm going to heat it. So I have boundary work, and that boundary work is leaving the system because the piston is expanding. So if I look at this, I want to go ahead and write my first law energy balance for it. So this is my particular system over here. I have the mass times U2 minus U1 is equal to the energy that goes in. And the only arrow I have going in is Q. And the only arrow I have going out is WB. So there's my first law energy balance. And I'm looking for Q. So this is the equation I'm going to use to solve for Q, which means I need to have some other way to find these other variables. So while the boundary work, we just did the whole other module looking at ways to solve for boundary work. And here we've got a constant pressure. So we're going to go ahead and use our equation for constant pressure boundary work, which is P naught V2 minus V1. So I need to know what those volumes are, but if I can get that, I can solve for the boundary work. And then U2 and U1. So what I need are some other properties. Now, looking here, I have a P and a T, and those are two intensive variables. And same thing at the outlet. So the state postulate says system's completely defined. I can go ahead and find U and V. I just need to go ahead and use an equation state or a table. And so here we're dealing with water. It doesn't say it's an ideal gas, so I'm not going to assume it's ideal. I'm going to go ahead and use the tables to go ahead and figure out what those properties are. So I've got a pressure of 400 kilopascals and a temperature of 250. So let's go ahead and look at the tables and figure out what our properties are. Okay, so here I'm looking at the superheated tables with 400 kilopascals, which is the same as 0.4 megapascals. And here I've got temperatures, and so I see right over here I've got 250 right there and 500. So, okay, so there I've got my properties. It's a superheated vapor, and this first column over here, this is little v. So I can go ahead and find the specific volume. So I know what little v1 is, and I'm going to look at 250.0.595 units on meters cubed per kilogram. And I also want to know the initial internal energy, U1, because that appeared in that equation as well. So I'm going to go over, and that's this next value over 2726. That's kilojoules per kilogram. And from that boundary work, I need the extensive volume, and so I have 2 kilograms. So I'm going to multiply 2 by 0.595 to get big V1, and big V1 is 1.19 cubic meters. Okay. Now we can go ahead and get state 2 as well, because it was at a constant pressure. It's also going to be at that, but now we're at 500 degrees. So we're just going to go down a few lines there, and V2 is 0.889 meters cubed per kilogram. U2, the internal energy, next line over, 3130 kilojoules per kilogram. Go ahead and calculate V2, which is 2 times 0.889, and that volume right there is 1.78 meters cubed. All right, so now we can go back to our first law equation. So we go back to our first law equation that we had, which said that M U2 minus U1 is equal to Q minus W. So there was my Q. Here was my boundary work that I had as well. Okay, now we need to go ahead and calculate the boundary work. So boundary work is P V2 minus V1. So that's 400, constant pressure, and then there's 2 volumes I just calculated on the previous slide. So 1.78 minus 1.19, giving me my total boundary work of 236 kilojoules, because the units on here are kPa, the units there are meters cubed, so that's going to give me kilojoules. And now I'm going to go ahead and solve for Q. So I'm going to go ahead and bring boundary work to the other side. Q is equal to M U2 minus U1 plus the boundary work. Let's go ahead and put in all the numbers that we have. 2, and then we had U2, so 3129. This was from the previous slide. 2726. And then I'm adding the boundary work, so I brought it to the other side, plus my 236. And that's going to give me my Q of 1043 kilojoules. So that's the amount of heat. So I was able to use the first law to go ahead and find out what that value of Q was. Okay, so this time let's do another problem. It's related, but just a little bit different. I again have a piston cylinder device with 2 kilograms of water. This time it's compressed. So this time I have boundary work going in. I'm given the initial pressure of 2.5 megapascals. I'm given the initial temperature of 300 degrees Celsius. It's a polytropic process, which means I have some heat transfer occurring, some Q, it's leaving, and the final pressure is 6 megapascals. Q2 is 6 megapascals, and I'm asked to find how much heat's leaving. So I'm asked to find this value of Q. And so let's write our first law energy balance. That's going to be the key here. M U2 minus U1, change in the system's energy, is the energy that goes in. So what the arrow's pointing in here is the boundary work, and the arrow's leaving is Q. So there's my equation, and that's where I can go ahead and solve Q. But I need to get these other terms somewhere else. And boundary work, we know how to calculate that for a polytropic process. Boundary work is P2 minus P1 over minus N plus 1. So I have both pressures, but I don't have either volume. But I have pressure and temperature. That's a pair of intensive variables, which means I can find little v1, which is big V1 over m. I have the mass up here. So So I can go ahead and find out what that value of V1 is. And then in order to find V2, well, I'm going to go back to that polytropic relation. It says that P1 V1 to the n is P2 V2 to the n. I'm going to have P1 V1 P2. I can use that equation to go and get my value of V2. So that's how I'm going to calculate what my boundary work term is. So okay, so let's go back here. Let's go ahead and start off. We need to get that value of V1. We're going to get that from superheated table. So I'm here at 2.5 megapascals, which was my initial condition. We pulled 300 degrees Celsius. There's my 300 degrees Celsius. And so my value of V1 is this first line here. So I've got V1 is equal to 0.0989 meters cubed per kilogram. And I'm also going to need U1, that first line energy balance. I'm going to the next line over. That's 2762 kilojoules per kilogram. So there I've got my V1 and my V2. And so I'm going to go ahead and do that to go ahead and solve for V2 using this polytropic relation. And what I'm actually going to do is P1 V1 to the 1.2 equals P2 V2 to the 1.2. And I'm going to use little v's here. And that's okay because that mass that appears on both sides to the 1.2 power is just going to go ahead and cancel out. So if I go ahead and put in my numbers here of my 6 and my 2.5 and this 0.0989, I can find out what little v2 is, and little v2 is 0.0477 meters cubed per kilogram. Get that from the polytropic relation. Okay, so now I've got v2, little v2, 0.0477 meters cubed per kilogram. So the only thing left now is U2, and I'm going to get that from this pair of intensive variables. Now I need to go to the 6 megapascal table. So let's go ahead and go to here's our 6 megapascal table, and recall that V2 was equal to 0.0477 meters cubed per kilogram. So let's go ahead and looking for 0.0477 and look, 0.0474. Oh, that's really close. I mean, that's within 1%. We'll go ahead and just use that value. That's going to get us within 1% of our value. So now I can go right over here to get U2, and U2 is 2893 kilojoules per kilogram. So now we can go ahead and plug all these numbers in. So let's go back to our energy balance. U2 minus U1 is equal to boundary work minus Q. Rearrange Q is going to end up being equal to, bring that to that side, so I'm going to have the boundary work minus M U2 minus U1. I need to go ahead and get my boundary work. Go ahead and calculate my boundary work, so I have P2 V2 minus P1 V1 minus N plus 1. I need to multiply all that by the mass. So I'm going to go ahead and plug in the numbers that I had on that slide there. That number comes up to 388. It's going to be kilojoules. So now I can go ahead and calculate what Q is. So Q is my boundary work, which is going to be my 388. Subtract my mass of 2. And putting in my values of U, internal energy, I have 2894 minus 2762. And that gives me 124 kilojoules. Okay, so that right there is the amount of heat that left the system here. Okay, so for the quiz here, let's go ahead and what I want you to do is to identify the correct energy balance. So let's say I have some shaft work that's going in. This is expanding. I have some boundary work in this direction, and I have some heat going in. So identify which one of these is the proper first law energy balance for the system that I just described here.